Just a second. All right, so hello everyone, and welcome to the electrochemical colloquium. This is going to be our last colloquium in this semester. And today we're discussing X-ray spectroscopy and how it can be used in the fundamental studies of solvents and electrolytes. So electrolytes, as you all know, play a very important role in electrochemical reactions. So they largely define how the ions and molecules approach the surface, how they leave it, and of course, electrolytes define the structure of the double layer, which ultimately affects the kinetics of charge transfer. And this makes it, in my opinion, super important to understand the structure and dynamics of electrolytes. So X-ray spectroscopy, which is also often called inelastic scattering, can give a fairly detailed picture of how molecules behave in the electrolyte. And so today we're discussing how X-ray spectroscopy can be used to study liquids and what type of information can be extracted from such experiments. Our speaker, Professor Alexander Föhlisch, is a leading expert in inelastic X-ray scattering, physical chemistry, and synchrotron radiation. Alexander received his PhD in Uppsala University in Sweden and did a habilitation degree at Hamburg University. Now he's a professor in the Department of Physics at the University of Potsdam and a director of the Institute for Methods and Instrumentation in synchrotron radiation research in Helmholtz-Zentrum in Berlin. So Alexander, thank you so much for joining us today. It's a pleasure to host you here. Now the stage is yours. We're looking forward to your talk.
Andrew, thank you for the kind introduction. And it's of course great to discuss these opportunities. And I think it's a fantastic way that we can do this here on Zoom. So not everybody has to travel all over the place. I just start my screen. And let's see, do you see the presentation mode or the other mode?
Not the presentation mode, the other mode.
Mm-hmm. This is Murphy's Law. How do we swap screen now?
Maybe you can try to stop sharing screen and reselect the right screen. That might be one way to do it.
I think that's what we have to do. Yeah, sometimes it's difficult.
It's okay.
Now cannot move over to your screen, which is just, it should do it.
Yeah.
Oh.
It's still the other side.
I think it should work. Yeah, I know, but I think it's kind of working its way.
Oh.
Is this the right or the wrong?
The wrong one.
All right.
You can click share the screen and just select the one that is the right one. It should be on a separate screen.
I did that, yeah. I just switched the share.
Mm-hmm.
Do you see the other screen?
No.
Come on.
As people
After
suggest,
2 years,
you can go to the presenter view and select swept view from top left corner.
All right. Oh, come on. Why can I not get back out of this? So I'm in Zoom, full screen speaker view. And why can I not share the screen with you guys? Here we have it.
Yes, it works.
Hold on. Yes and no. No, hold on. I'm still wrong. But I think we're slowly getting there.
It was correct, Alex.
I know it was correct, but it was like, here we have it. Do you have the right one?
1 second. I don't see so far anything. Probably it's loading. Can you do it again? Just once again?
Unbelievable. This is a difficult start here, but sometimes it somehow got stuck like hell. I just take the desktop. Maybe it works like that.
Yes.
You have, I mean, you have the right view.
Yes, the correct one. Yep.
That is awesome. Do you see my pointer?
I see your mouse. Yes.
That's fantastic. Okay, let's leave it like that. Thank you. My apologies. This is a nuisance, but I think we made it. So it is, of course, the principles of soft X-ray spectroscopy and the application to these molecular systems. And now I cannot forward my slide. No, I can. It's just very slow. And Andrew put a kind request when he said, well, why not get like an overview of what RIXS means, the inelastic processes, and what we learn from it. And then, of course, the mistakes or like the opportunities and the trouble which is associated with it. And finally, it would be fun to learn something about hydrogen bonded networks. And of course, embedded in the hydrogen bonded network is the active moiety, which does the electrochemistry, the photochemistry, or the thermal chemistry. And so I realized that this is a hell of a good job, but maybe I start a little bit on the fundamental side. So we really have like a great take-home message and further understanding. So in a nutshell, what makes X-ray spectroscopy really a fun thing to spend time with and to work with is that we have core levels in each atom, and the atoms are linking up. And this is in a way pictorially shown here by the shared electrons, which you could call the valence electrons. And that's actually an adapted picture by Kai Siegban, who got the Nobel Prize for electron spectroscopy with X-rays. And the point is, if we think that the core level electrons are completely localized on the positive nuclei, and the shared electrons carry all the interesting information, there is one way to link this, and this is the soft X-ray. The soft X-ray just has the energy to drive the transition between these completely localized electrons and the shared electrons, which really are important for chemistry and material properties. And if you so want, phrase it into a molecular language, X-ray spectroscopy or soft X-ray spectroscopy is really an atom-specific projection where we can bring all the relevant properties of matter, of molecular, of condensed, of surfaces, and project it onto the selected atoms by having these optical transition. In a way, it's really an equivalent to a linear combination of atomic orbitals, which we can achieve by using soft X-rays to project these different electronic states onto each other. Now, there are a lot of different kinds of spectroscopies, of course, and most notable, we always start in the ground state, which is just our system as it is. And then we have, of course, a photon, which is a soft X-ray photon, which can liberate an electron and will therefore then probe the holes in the occupied density of states. And that's what we call photo emission or a photoelectron spectroscopy. But of course, we can, as just discussed, also create these core excited states. Therefore, we gain this atomic projection. And then this core excited state again decays, and we get out fluorescence or X-ray emission. And so we have these other ways which are called resonant processes. And they are very important too, because as you see, we do link back to the same final states in some degree than what we do in the classical photo emission, which is a much more established technique. Now, the beautiful thing of having core levels is that they allow us to distinguish chemical species, which are otherwise in a way tricky to figure out in what state they are in. And that in a way is surprising, because as we said, the core levels are atomically localized and they really don't overlap to their neighbors. Still, they carry very, very strong dependence on this core level binding energy on the chemical environment. Now, this is already so in simple molecules. And if you, for example, here trace the different carbon atoms, which are in a molecule, which is here ethyl trifluoroacetate, you realize that the carbon atoms are, of course, in different chemical neighborhoods. Here we have a methyl group, right? I mean, 3 hydrogens. Here we have three fluorines. So it's quite clear that the electronegativity of the environment is different. And that is seemingly depicted when you look at the core level binding energies, where we realize that each of these different environments is reflected in a different binding energy. So we can really pick them up and differentiate them. And that, of course, makes it to a powerful tool. For example, if you do electrochemistry or photochemistry, because you see changes in oxidation state, changes in local charge environments. This works not only for one molecule, for a lot of molecules. And it is basically the core why people call this core level electron spectroscopy for chemical analysis, or ESCA. I think it's today less used, but I think it still describes beautifully the logic of it. And if you want to go to a surface logic, you even can actually distinguish when you, for example, an N2 molecule, which is sitting on a metal surface, you can even distinguish the inner from the outer nitrogen. And there already the trouble starts. Yes, we see 2 different lines. That's great, but it's a little tricky to say what is what. So that is then, of course, people have looked at a lot of different systems. You can kind of make some relationship between chemical shifts and electronegativity and various parameters. But the challenge is, of course, as an experimentalist, one thing is to measure things, another thing is to interpret them. And so I think for the audience here, it might be great to understand, yes, there is the chemical differences, but yes, we can also interpret them and understand them in a good way. And for that, we need to discuss a little bit the concept of what binding energy is. The binding energy and the shift thereof, the core level binding energy, we in principle have a very clear thought, and I think everybody would understand that we can look at it in 2 different ways. We can either take the total energy picture or an orbital-based picture. When we look at the total energy picture, we would say the system, also our molecule, our adsorbate, our electrochemical environment, has a total energy with n electrons in it. It's just a total thing. It's a macroscopic object. And then we remove an electron, and of course, that changes the total energy. And the energy difference is the binding energy this electronic system had upon removal of the electron. Conceptually, that's the cleanest way to define that, because, of course, it is the true energy it takes to remove from the total system 1 core electron. Now, in an orbital-based picture, you would like to draw this back onto a description of atomic orbitals, which we all know It's an approximative view at the reality of electrons and nuclei. In doing so, we say removing such an electron must cost the energy which it has when it's bound as a orbital in a Hartree-Fock type of logic. And therefore you set the binding energy of a specific electron which you remove as its negative Hartree-Fock orbital eigenenergy. That's what's called the so-called Koopman theorem. And in this, it's clear pulling out this electron in a ground state picture does not exactly do the job, because there's relaxation. I mean, all the electrons around it will say, oops, there's one missing. And then there's also correlation, which means a single electron actually also interacts with the other ones. It's not only flying around in a effective field approximation. And so thinking about the binding energy, when you read the literature, people discuss either in a total energy picture or in an orbital-based picture. And we should try to elucidate a little bit what this implies. So getting back to our example of the two nitrogen atoms sitting in a metallic environment where one happens to be closer to the surface to the other, in a total energy picture, of course, in the beginning, we have always the total energy of just having this molecule sit on the surface. And then we say, what's the energy if we ionize the inner atom? If we took away an electron from this nitrogen, we can kind of write this down. So the binding energy of having the inner nitrogen atom ionized is the difference of the total energy with all electrons in minus the total energy when the inner nitrogen atom has lost its core electron. Okay, easily written, it's correct. The same we can do for the outer nitrogen atom. Of course, the initial energy is the same. It's just the nitrogen molecule sitting on the surface. And then we take away an electron from the outer nitrogen, which is pointing away from the metal. This is also easily written. And then, of course, the change in binding energy when we compare the inner to the outer is the difference between inner minus outer. That's very simply written. We take these two ones, subtract them. The starting is equal. It gets it's 0. And so the difference is the difference between removing an electron from the inner atom or the outer. That is all correct, but it doesn't give us now an answer which line is what, because how do we get these energies? And that's where the trouble starts. How can we, if you sit there and you have like a certain molecule on a surface or in a compound, how can you try to get an understanding what do different peaks now mean? And this is a very powerful approximate way, can be readily used and gives very often already a clear explanation what's happening. And we're gonna walk it through. It's the so-called equivalent core or the Z+1 approximation. What does it mean? If you, sorry, it scrolls a little bit. If you take a nitrogen atom and you remove a core electron, all of a sudden the valence electrons see way more of the positive charge in the nucleus. Because of course, the core electron is like circling the nucleus in a tight orbit, and therefore it screens these positive charges. If you remove this core electron, all valence electrons seemingly reside in a potential which is like more positive than just nitrogen. And since you add a charge, a positive charge apparently to it, the core ionized nitrogen behaves like oxygen. And that means a core ionized nitrogen atom behaves like a valence ionized oxygen atom. It also means that the core ionized carbon atom behaves like a valence ionized nitrogen atom, and the core ionized oxygen atom like a valence ionized fluorine. So it's always in the periodic table the core ionized or core excited species has a chemical equivalence to the next element, the Z+1 element in the periodic table. This is the so-called equivalent core or Z+1 approximation, which greatly helps experimentalists who look at soft X-ray or X-ray spectroscopic data to get an understanding what they're looking at. And you could say after ionization of an atomically localized core electron, the positive charge of the nucleus is less screened. And thus, all valence electrons see the effective potential that corresponds to the next element in the periodic table. Let's do that now and illustrate this logic on our N2 problem on a metal surface. If we have the total energy of the ground state, that's the lowest energy. Then we core ionize. Let's core ionize the outer nitrogen. The core ionized outer nitrogen is as if a NO molecule was standing, because in the equivalent core approximation, we look at the core ionized outer nitrogen as if it was oxygen to great approximation. If we core ionize the inner atom, we would have the inner oxygen atom, inner nitrogen atom replaced by oxygen. Now it's quite clear, of course, from the logic of the electronegativity of these elements, that NO always binds on the metal surface with a nitrogen down. So this is energetically favorable, whereas this way around costs energy. And from that logic, we know that the energy difference between the ground state and ionizing the outer atom is a smaller energy difference than ionizing the inner atom. For that reason, we can assign the inner binding energy of that peak must correspond to core ionizing the outer nitrogen, also this guy, whereas the second peak here has a higher binding energy and it therefore corresponds to ionizing the inner nitrogen atom. And of course, we can write it. And interesting enough, in that system, the splitting of these two peaks is the energy it takes to rotate a NO molecule as a ON on this metal surface. So it helps us to assign and use the equivalent core approximation in a very efficient way to understand what are the leading terms and why do some split peaks occur where they occur. This is why the total energy picture, together with the equivalent core approximation or the Z+1 approximation in X-ray spectroscopy, is a powerful tool to get an idea what do these different peaks which you measure in core level spectroscopy mean. Of course, there is no orbital level type of assignment. For that, we need an orbital-based picture. And we said, in that we say, let's look at these binding energies as Hartree-Fock eigenvalue energies, also individual electron energies, plus relaxation and correlation terms. Now, that's also not exactly an easy deal, because in principle, you have to also still get for the correct binding energy, the total energy right and the energy of the total system. But of course, we can say the change of electron occupation is directly related to the single electron energy. And in doing this, we just get away being aware that we have these additional terms. We don't know them, but if we look at the relative differences in our molecules, we can say if we compare side A to side B, it's the difference between all these terms. And as long as the relaxation terms of a carbon atom sitting here or a carbon atom sitting there is similar, these differences just are lifted away because they are small. Equally is the situation with the correlation. And for that reason, surprisingly well, you can often, when you have like differences in electronegativity, get away with just comparing the different Hartree-Fock or Gaussian, I mean, depends on the program you calculate with, you get away with using the orbital eigenenergies, the single electron eigenenergies, and you look at them for the different molecular orbitals, and you get surprisingly good descriptions of the shifts of the core level energies which you measure based on the orbital eigenenergies. But the reason is really because the relaxation and correlation terms typically cancel out. It's not because it's a correct description, but it's a cancellation of terms which leads to the fact that ground state orbital energies have a meaning in core level spectroscopy. This is the simplest way to look at it. And in literature, you find a way which is equally powerful, which is related to that, which is basically an idea which was postulated by Slater and which is used on a daily basis, which is the Slater transition potential method. Here we say, again, the binding energy is this difference in total energy with all electrons or an electron removed. The binding energy is also the rate of change, actually the change of total energy as a function of electron occupation. And if we do that, we can simply say, let's just put that as like the electrons with an electron or without an electron, and then Taylor expand simply, sorry for the switching, which it does automatically. The Taylor expansion here of the energy we can just put into the first, second, and quadratic term with electron occupation. We just say the total energy should obey such a term. We can now very easily take the first derivative of a plus b n plus c n to the square to dn, which is dE over dN, which is b plus 2cn. And then we take the total energy for n equals 1, which is a plus b plus c, minus the total energy for n equals 0, which is just a. And this we have written here. This term we can easily solve, and out of it comes, well, that's just a fractional occupation of having half an electron in the core level. So interestingly enough, if you do a simple orbital-based calculation and you force the orbital to be half occupied, it gives you beautifully the energy of the core binding energy, which you measure in X-ray spectroscopy. The reason is that the slope of the total energy difference between the full occupied state and the one electron removed state, which is this line, is of course also matched at this point when you look at the filling of electrons as a function of number of electrons. Half fraction has here the tangential at exactly the same slope than the total energy difference. That is the rationale of the so-called Slater transition potential method, which says, let's calculate with a half occupied core level, number of electrons equals 0.5, and we get out of that actually the correct core level binding energy. And that is typically done. And so when you talk to computational people or physical chemists, and you say, well, look, we measured this and this binding energy in our different electrochemical states, in my different molecules, they will say, oh yeah, we calculate in a transition potential method where we just take half shell occupation. And in the first place, you think, what the hell is that? I mean, the shell cannot be half occupied, either the electron in or out. But this is exactly this trick to deal with the removal of an electron and the relaxation of the system, which is transiently occurring. Now, to make a long story short, if you want to, for example, then compare binding energy differences, for example, for water and a furane molecule, and you look at the oxygen, experiment shows a chemical shift of minus 0.8. If you say, let's take it frozen, simple calculation of the orbital energy, it's completely off. It's the wrong direction. It's not a great thing. But then if you do the transition potential, it gets the right direction and it makes everybody kind of happy. And that's why this is the way how we typically look at the core level binding energies, which are experimentally measured, and the chemical shifts when we compare to orbital based models. Okay, that was the thing. X-rays are great. They allow us to differentiate different chemical species in spectroscopy. We understand that the analysis, what it means, can be either done on the Z+1 or equivalent core approximation, or it is being done in computational tools like Gaussian, Orca, you name it, where you use the Slater transition potential approach of half-filled core levels, which is a great way to computationally effective mimic the situation of a transient core excitation. But the whole game is we project the valence electrons, which really create the bonds, which make the magnetic properties, which make all the collective properties onto the core levels. And by that, we learn about their localization or what matters where, and have this atomic specific projection of valence states. Now, as Andrew said, we should discuss RIXS and photon in, photon out, because with this thing, you can look deep into materials, you can deep look into electrochemical cells, you can really do that very well. And so we do two processes in close connection. We do the core excitation where we absorb the X-ray photon. And then we do also the emission where we decay and a photon comes back out. So we have the X-ray absorption and the X-ray emission, where each time you have an atom-specific projection between the core level and the valence. And doing that, we get what we call resonant inelastic X-ray scattering, which is the probability of absorbing a photon of X-rays, and then again emitting fluorescence or having an X-ray photon come out. And this is, of course, photon energy dependent. So if we scan through the excitation energy or the absorption axis here, this varies as a function of energy since we lift the core level into unoccupied state. And then depending where we lifted it, we can decay. And therefore, we get also an emission scale at each absorption point. So if we project the emission scale and say we don't care too much about it, we just measure the pure absorption scale, which we call X-ray absorption. But if we actually then look at the fixed energy and we look at the emission scale, this is what people call X-ray emission or X-ray fluorescence. In reality, it's always this coupled event, absorb and emit. And this is what we call resonant inelastic X-ray scattering, which is the correct way to actually look at X-ray absorption and X-ray emission, which are projections of this process, either on the absorption or emission scale. Doing this is actually a good thing, but it's also a very tricky thing. The trouble is, to measure X-ray absorption in the correct way, of course, we have to fulfill Lambert-Beer's law, where we need an optically thin sample and we measure the number of photons which get stuck in the material. So we have here photons come in, they go through a thin sample, and then we measure how many come back out. In liquids, we can do that by creating thin jets, which are like a few hundred nanometers thick. And then we really measure the number of photons coming through. And that's in principle the correct way to measure that. And we get the number of photons hitting an absorber. And out of that, we can get, in a correct normalization, the atomic cross-section of absorption taking place in the material. Often this is hard to do because you have a thick sample, it's bulk, whatever, and you have to measure fluorescence here. fluorescence yield is tricky because in fluorescence yield, you measure not only the absorption, but also the penetration depth. And so because the light coming in has more energy than the light coming out, there is often a mismatch between this ideal situation. And in the worst case, this can lead to a complete reversal of the spectrum, which we call self-absorption. Basically, what happens is the light going in is absorbed in a thin layer, and the light coming out is coming from a deep layer. And that's why you actually don't really measure the absorption in terms of what we want to do in Lambert-Beer's law. But in a way, you measure the variation of the depth of the field, how deep the radiation penetrates the material. This is done also no matter if you do total fluorescence yield or partial fluorescence yield. And whenever you do, therefore, a partial yield measurement where you don't measure perfect transmission, you are always suffering from that, which we have here exaggerated massively. And therefore, your measurement, which you do in fluorescence yield by shining light onto a solid and then measure fluorescence coming out, you can get rather good doing that in normal in grazing out, but you always suffer a deviation from the ideal situation. So whenever we measure X-ray absorption in these type of field techniques, we have to be very careful, and we should not be very lightheartedly assigning relative intensities to true absorption strength. But even though we have a deviation from the ideal case of absorption from the Lambert-Beer law, we still get very good signatures where are the absorption states, even in these partial yield methods. But everybody who's using this should kind of get acquainted with the issue of X-ray as X-ray absorption measurements and these type of aspects of what we call self-absorption. Now, if you do it right, it of course is a powerful tool. And for example, you can really assign from the absorption and the emission the orbital energies and orbital occupations as they are in a coupled system. Here it's a glycine molecule sitting on a metal. They have different oxygen atoms. They have a carboxylic carbon, a methylic carbon, a nitrogen. And you can really separate all the p orbitals on the nitrogen in different directions, x, y, z, to the surface for the occupied and the unoccupied by looking at the X-ray absorption, as we just discussed, but also then on the X-ray emission, as we will discuss a little more, which is the fluorescence. And the sum of it we call resonant inelastic X-ray scattering. We can project onto each atom the nitrogen, the oxygen, the chemically shifted carboxylic and methylic carbons, and from that get a very, very detailed view of chemical bonding on such a surface in various environments. As said, the process underneath, we always treat on different levels of complexity, trying to analyze either quickly, what does this binding energy shift mean in a chemical interpretation? What do my peaks mean in NEXAFs and fluorescence? And do I have to be careful? Can I just use these intensities and say that's the number of chemical species, or do I have to think about this and analyze a little more in detail to not make a mistake in the relative strength assignment? And finally, we always treat, of course, resonant inelastic X-ray scattering processes, which are, of course, so far simplified, dealt with. Because what it is a photon hits atoms and it loses energy and momentum. Why it's a resonant inelastic process. And if you want to be serious about it, it's of course a process which we describe in mathematically in the so-called in second order perturbation theory, which is the so-called Kramers-Heisenberg equation. We can understand that, and I think it's also just good to get a feel for it, because this is a mathematics between what we discussed. We absorb and we emit again. So the photon we shine onto our ground state, here's an atom, core levels valence electrons. This we describe as the wave function, which we call here 0 ground state. And this leads in a dipole approximation to a core excited intermediate state, which we call intermediate I. We just lifted the electron. That's what we did. Now, there can be many close-lying states because of vibrations or because of close-lying species, or you name it. So there's a summation over all reachable close-lying states. And of course, from that state, we also decay again in dipole approximation to a final state, which we typically call X-ray emission or fluorescence. So what we call X-ray absorption in dipole approximation is from O to I, and then X-ray emission is from the core excited state to the final state in dipole approximation, which is I to final state. And then, of course, we need to conserve energy, which is like here at the end. The photon energy we send in and the energy of the total system has to be in balance with the photon energy which comes out and the total energy of the system, because otherwise we would have generated electron. So we shovel optical energy into the system and we get out optical energy and deposit some in the system. Now, this process of absorption and emission is resonant, which means we have an enhancement of the cross-section because of the higher probability when they are finite states. And this we describe in a classical resonance term, which is the photon energy we shine in, the energy difference between ground state and initial state. And it's clear when this energy is just hit by the photon, we just overcome the energy it takes to create a core hole. And for that, this is odd resonance, and this term would become 0, and the probability for that to happen is infinite. Now we understand this infinite thing is not a great idea, and therefore in the scattering equation, we have here the so-called natural lifetime broadening, which is which reflects the fact that the core ionized state or core excited state doesn't live infinite. Everything which is excited has a lifetime, and the lifetime translates into a lifetime broadening, which in single exponential decay is, of course, a Lorentzian width. And this quantity is the Lorentzian width of the natural lifetime broadening. So that qualifies the width of the resonance which we're having. Now, of course, this equation works if the photon which we absorb leads to this resonant excited state, which has a lifetime, and then it says, oh, I fall back. And falling back into the ground state is what we call a participator. If we do in resonant inelastic X-ray scattering a process where we start in the ground state and we electronically come back, we call it a participator, and it leads to vibrational excitation, spin excitation, or orbital polarization excitation. Like a p electron which was pointing into X, then later points into Z. That's what one is calling a participator inelastic scattering process. We can also have a spectator process where we start from the ground state, we go core ionized into intermediate, and then we end up, because the electron we had lifted up doesn't decay, but another electron decays, and nominally we end up in an electron hole pair. This is what we call typically fluorescence or X-ray emission. In this language, we would think about it as a spectator, because the inelastic electron which has been lifted up is looking onto the decay. So the absorption step looks on as a spectator to the decay process with another electron. This is just only formal language because, of course, it's just a scattering event with all these different states are having probabilities to occur. All right, let's do something real, which is an experiment. Very simple. Take a molecule, which is now oxygen, could also be N2, Okay, this is now oxygen, but it's always the same. These two molecules have a energy as a function of bond length. And this is plotted here. That's the potential as a function of distance, right? It has a minimum, which is the equilibrium bond length. Shining on an X-ray lifts the wave packet into core excited. We discussed it. You could think of it like oxygen becoming a little fluorine-like. That wants to extend the bond, and it's doing this, and therefore the wave packet here in a way propagates. And during the lifetime, which is for oxygen, about 3.6 femtoseconds or 4 femtoseconds, this propagation happens. And when we then decay, all of a sudden, the wave packet is a little different, and we are starting to populate all these vibrational levels. That's a classical Frank-Condon problem, where we project the wave packet up, then there's wave packet propagation, and then it decays, and it creates vibrational progression from this change in the core excited state. So this progression we measure here is really the ground state vibrational spacing as a function in this potential. And the probability to go there has to do with the change in bond during the core excited state. And that's exactly what we measure. You measure in this participator channel the vibrational states as they occur due to the change in the core excited state. And then, of course, we also measure all the electronic losses. What we also note, and what is very interesting to understand when you think about RIXS a little more detailed, if we lower the photon energy, all of a sudden we see less and less vibration until we see something which we call vibrational collapse. It seems to be only a single line. Now, why is, oops, it shouldn't do that. Why is it doing that? If we give less energy, the case down here, we are in a way missing energy to populate the lowest state. And this is what is in this type of spectroscopy described as a detuning of the effective scattering duration time. You could think of it as an idea that, and I think it's wrong to do that analogy, but it helps in a first step. If we want to give less energy to the system than it needs to reach this thing, we can do it because in the Heisenberg approximation or Heisenberg uncertainty rule, energy and time is related. For a short time, we can have a little more energy than we need. And therefore, in a shortened way, we allow the scattering. We should think about what this means. In principle, it's of course a consequence of the scattering logic. We have a detuning of the nominal resonance, which we call omega. The detuning is the missing energy to lift the electron into the lowest level. So the photon energy we need is detuned by omega. And therefore, the photon energy which we put in is the nominal energy we would need to go there. And then we detune an amount minus, which is now plus omega, but omega is a negative number. We can put that in here. We replace the energy here by Eg plus omega. And then we have omega plus Eg minus the state energy I plus the lifetime broadening. This is just rewriting it, rewriting the photon energy as a deviation from the nominal resonance position. Now, if this detuning, the deviation, the missing energy to reach resonance is larger than the lifetime broadening, and also larger than the spacing of these vibrations, this is the leading term, and this term becomes big compared to all other. That's nice, because in that thing, this summation here, you can pull out, and you will remember the summation over all intermediate states becomes the completeness relation, which is like unity. And therefore, all of a sudden, we have in the scattering equation what we call a collapse to a quasi-direct transition. This is the single line we are seeing, and all the vibrations appear to be gone. Another way, and this is this time logic, is, well, we had the lifetime of the resonance as I gamma, the Lorentzian broadening, which is this complex energy. We can construct out of that not only a complex, but we could give omega to it. And we make a mixed energy. It's omega plus I gamma. If we do that, the lifetime of the state, which is of course tau plus h bar over gamma, we extend that with omega. And all of a sudden we get an effective scattering duration time, which is then the real detuning plus the complex and the phase. And those people who remember, this is the same thing like running a harmonic oscillator. A driven harmonic oscillator takes in energy when the driving field goes together with its resonant frequency. But if the driving field detunes, it sometimes is driving it in phase and then it drives it out of phase. So the time where the driving field is in phase with the oscillator gets less when you're detuned from the oscillator frequency. And that's exactly this point why the effective scattering duration time shortens when you detune in resonant inelastic X-ray scattering. That is a very, very general behavior of X-ray or light matter interaction, because resonant inelastic X-ray scattering is just another resonant Raman scattering approach. And this has been, of course, and is known also for the optical community, where optical Raman spectroscopy done when, in the 70s, when lasers came along, people realized that the scattering duration time of an optical laser changes significantly when you detune the optical laser away from your molecular resonance, because of the off-resonance driving of this harmonic oscillator. And so X-rays, RIXS, is really nothing else than a resonant Raman spectroscopy where the optical resonance is not in the visible, but actually in the X-ray, because we link to a core level. And I think it's very good to be aware of this connection, because from the underlying logic of these spectroscopies, RIXS and resonant Raman spectroscopy is mathematically truly identical. Now, the good thing is, maybe we don't have to deal with all of this because we have powerful tools. The conceptual view of core levels, chemical shifts, Z+1 approximations, the Slater transition potential, and the idea that X-ray absorption and X-ray emission, if we're careful with the detection scheme, really is an atomic projection of state occupancy and the vibrational, spin, magnetic, and orbital losses. And this works for gas phase, liquid phase, interfaces, and solids alike. But as said, underlying is the whole machinery of resonant scattering and light matter interaction, which is what correctly said, it is a resonant Raman spectroscopy, which in X-rays is called resonant inelastic X-ray scattering, and the underlying Kramer's Heisenberg relationship of second order perturbation theory. So with that, I think maybe we take a little break, people mill about it, and then we can continue with a little bit of a research example on what these probes learned about water and this type of issues in a little bit more applied way.
Thank you so much, Alexander. I think we're open to questions. 1 second. the audience can unmute yourself, so please feel free to ask questions if you have any, and maybe I can start in the meantime. So from, I have sometimes to ask questions from a very basic point of view, and maybe you will have to repeat a little bit this, but I think what might be slightly unclear is in RIXS, what is the scope of changing the incident energy? Because ultimately you're measuring the emission. So maybe you can just expand a little bit on that topic. And
Okay.
The main question is, so what is the reason for changing it so closely? So of course, if you change from one element to another, that makes sense. But if you're changing it with an EV range, what does it do?
Okay, you're right. And one way of changing the energies, of course, as we discussed, we have a molecule which has two chemical species. And you want to say, well, let's now pick up the atom, which is like in a very electronegative environment versus the atom, which is in a positive or neutral environment. Then, of course, you tune onto the different core resonance, and therefore you project out these different species. As we just discussed, in the scattering process, there are a few femtoseconds time. And if you have light elements in it, like protons, in your measurement process, your molecular species might move. And so you measure the chemical species undergoing structural change, and therefore your X-ray emission spectrum contains actually the distorted species as it has evolved in the few femtosecond scattering duration time. Now, that is a problem because then you don't actually measure how it was when you wanted to actually have it in the beginning. If you now detune your photon energy within this resonance, what we call onto the, the leading edge, so you go a little lower in photon energy, the scattering duration time gets shorter. And therefore you don't allow the molecule to actually change its shape. And you measure then the electronic structure in this detuned version without having undergone structural changes, right? And that's often a trick to separate. Why do we see these spectral features? Are they a result of the scattering process, which gives an intrinsic distortion? And we can cross-check that by detuning, and then we see the true initial situation without suffering the X-ray induced femtosecond dynamics also taking place.
And when we collect just an XES spectrum, that just integrates all the sort of energies, or in some way you can see it as... Okay.
That is, if you measure X-ray emission or X-ray fluorescence, you truly have all potential structural and electronic or spin excitations which occur in the natural lifetime present in your fluorescence spectrum. And there have been, and I'll show that on the example of water, there have been massive misinterpretation based on that, because people thought the additional states which come up are present in the ground state of the system, but it turned out that really they occur because in the X-ray fluorescence, there is so strong distortion that if you measure this just non-resonant, you really collect a huge signal from the modified material and not actually the material as you would get it if you detune and shorten the interaction time.
Okay, no, that explains a lot. Thank you so much. We have a question from GD.
Okay. Hello.
Hi.
Okay. Thank you, Professor, for your nice presentation and a nice talk on this soft XAS. So I do have some questions regarding of the soft XAS. The first question, can we identify the atomic orbital depending on the soft XAS results? For example, for metallic atomic orbital. And the second one, what is the main message on the difference of the binding energy of the inner and the outer shell of the peak? For example, for nitrogen, we have to take some energy difference or the total energy from the picture. So what's the main message? Or can we identify some of, or can we say the difference energy is regarding of oxidation state or the message or the main message? And the third one is depending upon the two types of energy, which is fluorescence and emission. So which one is the most or the main basic important for the identification of the surface? I mean the oxidation state regarding of the valence state. Thank you.
Thank you. This great question. I think there are three of them. The way I was trying to discuss it was like from a pedagogical type of viewpoint. And think about the N2 problem comes, of course, if you want to do nitrogen fixation catalytically, right? Because then the question is a nitrogen molecule standing up or actually lying down on a catalytic surface? And if you want to understand what happens if you actually want to split the nitrogen molecule, which is a very hard thing to do chemically, in what coordination to the transition metal does this actually happen, right? And this is often the question. So the fact that having different coordination of a molecular unit to a metal center is visible in different binding energy has been historically helpful to understand in what geometrical arrangement does the surface chemistry of nitrogen occur. Does it lie down? Does it stand up? And this type of argument. So, of course, I showed the thing as an example where you understand that even though the differences seem to be minute, because you could argue, is it a big difference if the N2 is standing, lying, or whatever, or does it have an angle to the surface? All this information you get out of the thinking about the core level binding energies, right? If the molecule was lying down, or it transiently is lying down because it rotates and it kind of connects differently to the metal catalytic surface, of course, the binding energy shift goes away. And from that, you know that. So the same you can, of course, do for any chemical reaction. You see how these, I mean, when you do an experiment, you say, okay, we have a starting point, a product adduct situation. And the first question is, how many different species do we have in the product and in the adduct, right? And then secondly, if we do it transiently, is there anything coming up in between? And so if we can identify, so what is it, right? So of course, when you use it as an analytic tool, you are watching for different chemical species to occur, and don't a priori say, well, they are different, now let's see how they look different. But you see how a chemical change of environment, a molecular rearrangement actually takes place. And your second point, of course, you can look at the metal edges. The metal edges are, in principle, completely identical. They are a little trickier. As we know, the D electrons, the F electrons, they have more correlation, right? So they're, from the point of electronic structure theory, a little harder to deal with. But in principle, everything which has been said here is equally correct. And indeed, when you look when you measure X-ray spectral information on, for example, the nickel edge, you can also describe the spectral information by the Z+1 element, which is then copper. So the Z+1 approximation equivalent core holds equally for the light elements and the heavy elements, where, of course, the D elements and F elements, in addition, have significant contribution from so-called multiplet and spin states, because the electrons couple to different S, L, and J values. And that creates a rich multiplet structure, which makes it not as easy to, by rule of thumb, just assign peak energies to a single line, right? Because if you have a high angular momentum, you get a lot of different relative orientations of that state and a lot of what we call multiplets. So a single electron line becomes like a lot of different lines, which are all related, right? But in principle, it's the same. It's just a little more crowded.
Thank you.
Thank you,
Anas,
Professor.
I think you
Thank
have
you.
your question too, and maybe we can continue.
Oh, okay. Is it? Hello, Andrew. Should I ask my question directly?
Yeah, Peter, either you or Anas, or you, it's okay. In either order.
Yeah, okay. Let me just continue since I've already started. Prof, thank you for very interesting lecture. I was a bit confused. Well, I didn't really understand it very well. Where you talked about participator and
Yes.
spectator. So and then I didn't really get, what distinguish this and when do they occur, and what are the fundamental things that that leads to this. I couldn't get it.
Let's explain that. That's very simple. Sorry for not being clear on that. It's just important for you folks because people use this terminology, and it's just, I guess, when you want to interact, it helps to have a sense of these things. The logic behind is simple. If we do X-ray absorption, we lift a core electron into the unoccupied states, right? Yeah. And then the same electron, the electron which we lifted up, can also just fall back. And then it participates in the decay. As it has been lifted up, it creates the core hole, and the same electron falls back. This is what we call a participator. Okay. In a resonant process. The other option is we lift up an electron from the core to the valence, and this electron sits in this state where it has been lifted into, and we would say another electron decays. And this we call a spectator, because then the electron which we lifted up in X-ray absorption is thought to remain there, and another electron falls back, and then this initially excited electron looks on. It's a spectator. It's an onlooker to the decay. This leads to different final states, because then you have an electron hole pair in the final state, right?
Yeah.
That's what we either call electronic loss or electronic excitation, but it's also called the so-called spectator, and it differentiates. So each time we have a spectator, we call that electronic loss or fluorescence or X-ray emission. But in the scattering picture, it's very clear why these are different things. Because as said, in a spectator, we lift the electron, another electron decays. Of course, it creates an electron hole pair in the final state, which is then an electronic excitation. And that's a different thing than when you look at the vibrational excitation or a spin excitation, because then this electron has been lifted up, it decays back, and the system has then all of a sudden a different final spin arrangement, or it has a different vibrational arrangement. And this is what one calls then a participant. But in the end, it's for you to understand when people say, yeah, we measure vibrational excitations or spin excitations, or we measure electronic loss or electronic excitation, or they call it fluorescence or X-ray emission, it's always the same scattering process, which you can differentiate conceptually in having the electron go just up and down and have a few femtoseconds hit a spin or a phonon or anything? Or does it actually really get up, get stuck somewhere, something else falls down, and you get out different information?
But is it already known for every system, for example, which of the process will happen? Because that will determine how you analyze the final result. So that is my point.
The thing is, typically, it's because the scattering is this quantum, I mean, it's really this, there's the sum over all possible states. It's always a probability what is dominant. And as Andrew pointed, this is why often we detune and we try to change the interaction time by not only measuring on resonance, but detune a little lower, because that quenches all the processes which take time to happen, and you basically purify to the processes which are already there purely by electronic excitations. So we can quench away the structural excitations, a lot of the spin excitations, but we only see electron hole pair excitation, which you would say is the most pure fluorescent spectrum you would get. Some people call it Herft. Also, there's a lot of terminology depending on to whom you talk. But the underlying logic is when you change the photon energy across a resonance, you change the balance, how long time you give to the process. I'm sorry, there's no real quick fix in saying, you know, it's all, in principle, it's a done deal. But when you measure, you gotta be careful in looking at what you see. Seeing two peaks could be two chemical species in the beginning. It could be one chemical species which has a high probability to structurally distort in the process. And this you would separate by changing the detuning and looking, does anything happen and what does it do?
Thank you very much. Very clear. Yeah, thanks.
Thank you. I think, Anas, if you have a quick question, please go ahead and we will continue.
Yeah, thank you so much. Thank you, Professor, for your insight for the X-ray spectroscopy. I have a question, and I'm a chemist, so I might sound naive to you, but still. So when you talked about detuning of the scattering process, so does it have anything related to quantum mechanical tunneling? Because it seems like that to me, because of the electron is going from one region to another, which is forbidden in terms of energy. So is it quantum mechanical tunneling, the detuning that you talked about?
This is a very smart point you're making.
Yeah.
Strictly speaking, no, but it is used in order to do such a probe. I mean, this is called the so-called core hole clock spectroscopy. What people do there, but this is what, when people do resonant electron spectroscopy. In resonant electron spectroscopy, you also have X-ray absorption, where you simply lift a core electron into the unoccupied density of states. Also you create a excited electron. Now, this electron can actually tunnel or hop to a neighbor. For example, if you have a sulfur atom sitting on a surface, it could either stay on the sulfur atom and decay back, right? But it could also hop into the metal substrate and do a charge transfer process. And then, of course, it is not available for decay anymore because it has delocalized, which is a classical charge transfer, which is the so-called, Marcus or Marcus-Föhlisch theory of electron charge transfer. And so, because the excited electron can either remain atomically localized or coupled to an internal continuum, which can be tunneling, which can be also hybridization, you have always next to the classical atomic channels, the channels which are what you would call the tunneling, which has to do with the rate of delocalization in the core excited state. And this is a whole field in itself, which is called core clock spectroscopy or charge transfer spectroscopy, where people use that to measure the rate of delocalization on very fast time scales. It's a powerful way, and it exactly uses this equation and the fact that you have what people would call dephasing or the coupling of a atomic orbital population to other density of states, either by tunneling or in a hybridization process.
Thank you so much. Thank you.
Thank you for an excellent question, Enes. Alexander, I think we can continue. Thank you so much for taking so much time for answers.
Yeah, it's fun. It's always fun to discuss a little science. Now, the trouble is, because Andrew said, why don't we discuss all of these things? And I said lightheartedly, yeah, why not? I realized that this is a hell of a lot of stuff. And so, but maybe I thought, let's focus a little bit on water as a solvent, which is clearly important for electrochemistry. And I think there has been a lot of evolution in the last years, and it's actually still ongoing, which is partly surprising, but I think it has really resembled a lot of aspects which even go to this whole debate of water splitting and how do we have to look at these things on a molecular level. Now, underlying is, and for some of you, this might be surprising, for others, it's obvious, there is still some controversial aspects on how should we look at liquid water in terms of its molecular constituents. For one, of course, one laughs at it and says, I mean, the water molecule, it's oxygen and 2 hydrogens. There is absolutely nothing one can say about this anymore. It's a 3-body problem. We know it's orbital occupation. I mean, it's a done deal, right? And it's true. We have a bending motion, we have a symmetric stretch, and we have an anti-symmetric stretch. Sorry, that's wrong. It's not asymmetric, it's anti-symmetric. And that's what it is. Now, the thing is, when we do liquid water, it gets somehow burdensome. And there have been different structural models put forward how it would be. The whole trouble starts, of course, with the anomalous properties of liquid water in the first place. The most obvious is that when we cool a gas, the gas becomes a liquid, and in doing so, it gets a higher density. And then if we make the liquid colder and colder, the density should raise, and finally it should solidify and get even more dense, right? And as we know, water doesn't do it. I mean, the frozen form of water is ice, which is swimming on the liquid, so it has a lower density. That is not nice. And it is a significant deviation from a simple liquid, and it leads, of course, to the density maximum at 4 degrees, where liquid water is densest, and so on and so forth. There are a bunch of other anomalies, which is the isothermal compressibility, which around 46 degrees has like this minimum, which it shouldn't have. The isobaric heat capacity, a lot of these things, and it has been studied to death why on earth it is. Now, we are not alone in this endeavor, because Wilhelm Conrad Röntgen himself, he was trying to model the deviation of liquid water from the ideal liquid. And the way he kind of tried to get out of this problem was by simply postulating, why don't we say there are 2 liquids in it? The liquid water could be a liquid A and a liquid B, which is kind of somehow in there. And as you change the temperature, they interconvert. So in the beginning, you are B-rich with little a, and then you are changing the temperature, and then you are A-rich with little b, and so on and so forth. But he writes himself in his manuscript that he hates the idea that invoking, in a way unprovoked, to say there are two waters, which, I mean, apparently it's a single liquid. It's like not milk and water. It's not like oil droplets in water, right? It's obviously a little bit of a thing. So he has been, for one, said, let's just model it. On the other side, he said, it's somehow not a nice thing that this is somewhat such a strange construction. And later on, people then try to get this thinking on a more molecular level, and they got away with a point. Why don't we just say we could construct an idea of having a fourfold coordination? So each water molecule has basically two neighbors through the hydrogen bridges, and then on the other side as well. So then this would be one type of density, which we could call one kind of liquid. And then we could think, well, we could also construct somehow a chain-like or ring-like thing, which has a different density. So people have been thinking, maybe this is a reason why that is. And then, of course, we know that in the liquid phase, the protons are hopping. The hopping time of a proton in liquid water is about 1.7 picoseconds. There's always fluctuation. So should we now think about that as a totally statistical process, or should one think about it as really a structural motive of rings and chains versus the other one, as the real true liquid logic? And the debate is ongoing forever, and one can, of course, think about a lot of studies all over the phase diagram. And if you're hard about it, there are various views of the world on that. What is underlying the issue? Underlying the issue is a really tricky aspect. And it has to do with what we call the so-called supercooled region. Now, here's pressure, there's temperature. That's obviously easy. So, of course, there is the gas phase, right? If we raise the pressure, it turns into liquid water. We agree. If we lower the temperature very much, we turn into ice. And actually, there are two different, there are a lot of different ices, but there are two different amorphous sorts of ice. One has a higher density and one has a lower density. These are the glassy forms of ice. So-called low density amorphous ice, LDA, and high density amorphous ice, which both exist, and they do a phase transition when you change the pressure. Okay, when you now melt them, okay, you melt. Now there's a crazy thing. If you take liquid water and cool, and it's a very clean liquid water, you can create a supercooled situation. The stuff stays liquid even though it is colder than 0 degrees. I mean, it should be frozen, but it's not. And it has to do with the fact that, as you remember, frozen water, ice, is swimming on the liquid because it has a lower density. So when you want to make out of liquid water ice, all the molecules has to get a bigger distance in order to freeze. So they have to expand the volume macroscopically. And as you make them colder and colder, their energy is less and less. They move slower and slower. So in order to gain more space macroscopically, they have to really move. And making them colder and colder allows them to move less and less. That's the reason why you can supercool such a liquid, and it remains liquid even though it's actually too cold to be liquid, right? It should be frozen. This is first the region of the so-called supercooled water, which then separates again into regions, which is the so-called heterogeneous nucleation region, where you have a salt atom, a chlorine, or whatever. And this thing serves as a nucleation seed. It's the seed of nucleation, which actually takes place to start a crystal. It's very much easier to crystallize when you have a distortion, which could be a surface, which could be a wrong atom. And this so-called heterogeneous nucleation is the way where crystal growth starts to grow. Now it's funny, because if the water is extremely clean, you simply don't have a thing where it starts to order. And this is the region of homogeneous nucleation. And then, because the water molecules are these objects, oxygen, hydrogen, hydrogen, a symmetric distortion of them is already a distortion which starts nucleation. So this is the temperature where only internal degrees of freedom, which are vibrations, can start nucleation. That's the region of homogeneous nucleation. Conceptually, it's extremely hard to measure in the supercooled region. That's why it's called no man's land. It's experimentally very, very hard to get there, because you cannot stabilize that region, because the intrinsic vibration wants to lead to crystallization. And in this region, we think, or one has to think in a way, that there should be high density liquid and low density liquid phases, which then should lead to a second critical point of water, and it should continue. This is the underlying problem of why liquid water, as we see it in the glass, could inherit properties of this hidden supercooled region, which somehow has to negotiate these volume changes, which are definitely there. And it has huge implications, because it could well be that in the upper atmosphere, for example, where we have droplet formation, it's very cold. If you fly with an airplane, it's minus 50 degrees. You read on the temperature there, and you say, wow, it's cold outside on the other side of this airplane wall. And you look outside and you see clouds. It's not clear so correctly. Are these droplets there actually supercooled liquids, or are they actually ice crystals? A lot of it speaks to it that maybe up to a third is actually supercooled liquid. And that would have huge implication on, for example, modeling the solar albedo. I mean, how much sunlight is actually reflected from an ice crystal, or like a liquid droplet, which is high or low density liquid. So there are a lot of issues which are related to that. And equally, at an interface, should we think of it as like a high density or a low density arrangement? Or if you want to do water splitting, and we have like intercalated water in like an anode or a cathode arrangement, how do we deal with that? How do these molecules link together? So this is a very tricky business, and it's very hard to get a handle on it. Now, interesting enough, the problem of like these anomalies is not purely unique to water. It is actually, and Angel, he, I think, did a great job in really conceptualizing this in a broader way. If you think about it, whenever a solid is crystallizing in a tetrahedral arrangement, also in a four-neighbor tetrahedral local structure, that is a very space-consuming crystal lattice. And when you melt that, the liquid is denser. And interesting enough, this behavior has, of course, ice, also silicon, gallium arsenide, germanium, many phases of diamond. And these density anomalies have massive repercussions. For example, silicon. In silicon, we all know if you want to grow a silicon crystal, you cannot just pour liquid silicon and cool it because it turns into amorphous silicon. The reason is, if it's cooling quick, the atoms don't have time to take up a space-consuming lattice. That's why they kind of get shock frozen into a denser form, which is the low density or high density amorphous solids, which is classical amorphous silicon. And therefore, if you want to grow a crystal, you have to do it very slow in this Kochalski process, where you take a seed crystal. The seed crystal starts to organize the liquid to gain a more space-consuming structure. And then you very, very slowly pull out the crystal out of the liquid. And at the interface, it keeps on piecing together the space-consuming lattice. This is the problem of growing great silicon crystals, or gallium arsenide, and you name it, or diamond for the matter. Now, we said that's interesting because the physics of ice and supercooled liquid ice and so on and so forth is obviously related to the physics of any tetrahedrally bound solid and its phase diagram. And so what we did there, we used X-ray spectroscopy to differentiate in a first step in silicon these different phases. In silicon, it's easy. Crystalline silicon, we all know, is a semiconductor. So it has a band gap. And the high density liquid silicon, which is just molten silicon as it sits in a molten duo, as a vessel, is the high density liquid, it's metallic. The interesting thing, the low density liquid phase, which can only exist transiently, is a so-called semi-metal. And so the spectroscopy with X-rays, which traces the occupied and unoccupied by X-ray absorption and X-ray emission, can pick up these different phases. So what we did exactly these absorption and emission measurements on silicon, and we melt it with an ultra-fast laser pulse, and then detect the chemical state, if you so want, or like the situation of the silicon atoms as they undergo melting. And in doing that, you see here's a time delay. Here's a semiconductor, there's a band gap. Then the laser shines on, we lift up electrons. All of a sudden, here you see electrons which have been lifted from the laser. Then these electrons seem to lose energy, they come down. And in doing so, the valence kind of shifts and becomes half metallic. And then it takes more time and it becomes metallic. So from this measurement, where we use X-ray absorption, X-ray emission in a time-resolved way, you could really see that indeed melting a crystalline silicon sample leads transiently to a low-density liquid, which then converts into the equilibrium high-density liquid. That's fun. Now, of course, you want to do that with liquid water. That is tricky. Because liquid water, the two hypothetical different phases, they are not like metallic and semiconductor. Liquid water is a transparent liquid. I mean, it definitely, it has a HOMO-LUMO separation, and there is no massive change. So what we thought, we can play this game with these vibrational energies, because in this inelastic X-ray scattering in RIXS, we measure all these losses, the distortions of the molecule in the scattering event. And if we now take the water molecule and excite it into the different X-ray absorption resonance that it has, you can actually drive selectively either this anti-symmetric vibration, the symmetric vibration, or the band vibration. And out of that, we can actually reconstruct beautifully the potential energy landscape which this molecule sees. These measurements has been done at the Swiss light source. So I think PSE, the infrastructure you have there has been crucial to do that. And we can therefore could measure experimentally this potential surface. That's of course fun. And you can do that not only in the gas phase, but also now in the liquid phase. And here you see, well, these are the X-ray absorption. Then you measure the X-ray emission, and you detune. You see the collapse because the scattering duration time shortens. Then you allow for a lot of time. Then you get into the next resonance. There are no peaks. You have no time. Then you have time. And so you can play these games both in the gas and the liquid phase and really try to understand what on earth does it now mean in terms of the electronic structure of the water molecules being stuck in this situation. And now we can, of course, analyze the data and really try to understand the electronic structure of the molecules. In the gas phase, it's rather simple as a function of a coordinate, which is here the asymmetric stretch, the deviation from equilibrium. We get beautifully the potential energy surface on which these molecules live. The same we can do in the liquid. And in the liquid, you learn that there are a lot of different potential energy surfaces on which these molecules live. But what you also notice is that really, it's not like we have two different potentials. If you would think that in the water network, there is like a region where the molecules have chains and rings, and there's a region where they are like in like more a tetrahedral arrangement, then you would have two classes of potentials. Potentials which are ring and chain-like, and potential which would be like, three-dimensional. And that one clearly doesn't see. So it's not like there are different patches at room temperature, like milk, where you have like oil patches and water patches. So we don't have like water patch A, water patch B, but the fluctuation, which is always from the protons hopping back and forth, obviously washes that out into a rather huge variety of potentials. And I think that has been insightful. And of course, you can correlate now these potentials and how they evolve to distances which we know from neutron scattering, where we can look at the oxygen, hydrogen, 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 oxygen, oxygen average distances and try to understand, so where do these potentials start to change at what correlation? It's a little too detailed to go into all of that. But in the end, of course, one can analyze hugely what do these potentials mean, how do they relate to all these spectral signatures. And if you want to do it on that level, of course, it becomes very specific. But it's quite clear for someone who is doing electrochemistry, water, solution, interfaces, it's interesting to understand that most likely we do have a rather continuous fluctuation situation, which then undergoes in these Helmholtz layers some ordering, but it's not like you really seem to have like directly inherent ordering patches within the liquid water itself. Of course, we looked at that in greater detail across the phase diagram of water and ice and gas, which is here plotted, the pressure, temperature, and the many different phases of ices, solids, and I mean, you name it. And of course, we wanted to understand, so what is now finally the number of oxygen-hydrogen bridge bonds in liquid water at room temperature. I mean, the stuff which we deal most of the time with. And people have been previously postulating that there should be 1.2 donated and accepted hydrogen bonds. Also, you have to multiply by a factor of 2, which is then 2.4 neighbors, if you so want. That's far away from 4 neighbors of tetrahedral. And since Andrew said we should also point out risks in the spectroscopies, how did that come? People measured X-ray absorption in these systems for a long time. And since X-ray absorption takes time to measure, they always measured from the oxygen edge a little below, and then somewhat up to 540 or so. You see this region. That's the typical range which people measure when they measure water X-ray absorption or NEXAS. And then they thought, here is the continuum. So in a way, we should normalize this all to the same height. And in doing so, sorry, it keeps on flipping. In doing so, you make a huge normalization mistake. So what we did then, let's revisit that. And we measured a very, very, very long spectrum. And you see, of course, if the photon energy goes very far above the resonant absorption edge, at some point, we just hammer out the core electron into the continuum. And it doesn't matter in what chemical state the oxygen atom was. The electron just flies away very quick. We call that the sudden limit. And in the sudden limit, the probability of X-ray absorption really only counts the number of atoms where it absorbs. In that case, the number of oxygen atoms in the sample. So for that reason, independent of the phase, solid, liquid, gas, I mean, you name it, this is 1. And you also see that beautifully experimentally, measuring so long out, really all these curves coincide. When we said that to the ESRF in Grenoble that we want to measure so long, they said, that's boring. There's nothing to learn. And we said, we want to do it nevertheless. And we could finally do it. And the amazing thing is, once you normalize like that in this correct manner, which is typically not what you do in the experiment because it takes a ton of beam time to measure this data. We realize, oh my God, all the normalization in this short range was wrong. I mean, the last 20 years, people have been normalizing at 540 and said, this has got to be the same height. And it just multiplied that into 1 and then compared the intensities there. And out of that came this really underestimation because they said, if this is 0 neighbors and this is 4 neighbors, this is liquid water, which should be the 1.2. And we said, oh my God, that's all wrong. We have to normalize high up. And then we realized the true number of hydrogen bonds in liquid water at room temperature and ambient condition is actually 1.74. So multiply by 2, these are 3.48. So it's way more towards tetrahedral. Tetrahedral would be 4 neighbors in ice. So liquid water at room temperature has 3.48 neighbors and not 2.4, which has been thought for a long time. And I bring that up here scientifically. The only thing which matters is, okay, it's 3.44 or 3.48 neighbors in liquid water, and it's good to know because it means it's much more space consuming. It's not rings and chains. So when we model this and we maybe want to study water splitting, that's what we have to start with. And for that, it's an interesting number. But the reason is, and Andrew said that we should also discuss pitfalls. When normalizing X-ray absorption, you got to really think, how far do you have to measure up? And the reason why this is the peak here is actually the scattering resonance of the second coordination shell in liquid water. You have a molecule which has a first shell of other molecules and a second shell of water molecules. And the electrons which we excite, they can kind of scatter within these shells. And amazingly, the second shell, which is this resonance, leads to this intensity. In gas phase, it's absent. Because of course, in gas phase, there is no coordination shell, and therefore there's nothing to scatter. In ice, it's very strong because it's highly ordered. And in liquid, of course, the second coordination shell also is there. And this was the reason why this normalization was so completely wrong, because people thought the scattering in the second coordination shell shouldn't be important. And of course, I mean, at first sight, you would say, well, that's plausible. But, you know, assuming something plausible doesn't mean this is how it is. And so only checking it out and going really high up where all the atomic cross-sections just coincide allowed to identify them. So that was 2019, and I think it was a relevant insight that the number of neighbors is really 3.48 and not 2.4, which is a huge difference. Another thing which people in X-ray spectroscopy have been dealing with water also for a long time, and which thought is an indication of these two different types of species in really a macroscopic sense. We discussed already here these vibrations, right? I mean, you remember. And what people really thought, if you measure here X-ray absorption, that's what we just discussed, the XAS and the second shell scattering resonance. People also realized, even though the water molecule has only a single peak, I mean, the HOMO, the highest occupied water state, right? When you measure X-ray spectroscopy on it, there are two peaks. And so people said, well, that's fantastic. One peak must be the rings and chains, and the other peak must be, you know, the fourfold. So very easy. We see it. And there have been a lot of papers on that. You know, rings and chains, mixing in alcohols, interfaces, in polymers, and this and that. But they forgot one thing. They forgot that the X-ray scattering takes a few femtoseconds. And the protons move during scattering. So what you realize when you detune, and we actually shorten the scattering duration, as we discussed before, these two lines disappear and there's only one line left. And so, as a matter of fact, the whole discussion about having two lines for the HOMO in liquid and water was actually the misunderstanding that the scattering duration time leads to proton dynamics. And one of these peaks is just a molecule, and the other one is the molecule when the proton is flying away. And of course, we modeled that in a little more detail. And in the theoretical model, you can look at that and say, let's set scattering duration time is 0. The photon absorbed and emitted takes no time. If we do that, we measure the lowest energy, the next state. I don't want to go into the orbital nomenclature here now. And then if we switch on time and say, let the proton suffer the core excited state for a certain time, 2 femtosecond, 4 femtosecond, 6 femtosecond, 8 and 10. You see that really the distortion leads to a second peak. And this you can now quantify. You can say, okay, what is the leading term? This is the oxygen on which we scatter. We can elongate the long OH bond. And if we do that as a function of time, we see that it's super sensitive. We could also elongate the short bond. this is also a little sensitive, but less. We could vary the neighbor to the long hydrogen bond, which is a little sensitive, but minute, to the shorter hydrogen bond, which is there, to the distance or to the angle of tetrahedrality. And from this analysis, you realize, oh man, this split peak is for the core lifetime, which is for oxygen, 3.6 femtoseconds. It is really the bond elongation in the molecular species during the scattering process. So the X-ray fluorescence or X-ray emission split peak is really totally not a signature of water having these two patches, as we discussed and as Röntgen originally thought in a way. So it seems like we gotta really think of it way more as a fluctuation problem of continuously changing coordination and not as a patch problem. You understand this type of basic understanding, what is the chemical nature of water at conditions which is relevant to electrochemistry, to water splitting, to solvation, to solution chemistry, complex chemistry, you name it, is important because we realize that we struggle with basic understanding on that level. What is the structure of liquid water? It stems from the supercritical, supercooled region, which is common to all liquids and solids, where the solid is tetrahedral and space consuming, which is silicon, gallium arsenide, germanium, diamond, and ice and water. And therefore, it is a very general theme. And it's just amazing because we have to really reflect on that when we do electrochemistry, charge injection in aqueous solutions, charge separation complexes, but even issues like what is the nature of droplets in the upper atmosphere, which are in the supercooled region. And for that reason, of course, we do research not only on these very basic things, but we have been building dedicated machines, which are now in commissioning here in Berlin, which are purely optimized to look at solution chemistry with inelastic X-ray scattering. We've been building the Heisenberg-RIXS machine at the free electron laser in Hamburg, where we can do all these things. These are the vibrational spectrum, and this is the split peak of water measured at the XFEL. And then we can, of course, see how this happens on a femtosecond time scale in pump probe, when electrons go in, when coordination restructures. And here you see first time resolved experiments where we look at iron trisphipyridine, which is a great charge injector into the liquid, and we look how it changes with time. It's just at the beginning. It's very exciting times, I think, with these tools now, because we start to understand for the solution for water, for the interaction of electrons with water, not only the chemical shifts, but also the scattering duration time, the dynamic aspects, how it influences the potentials. We're getting at the really molecular level understanding of the liquid water and its properties and its chemistry way better. And it's just, I think, super exciting. I try to summarize and not kind of mill on further electrochemistry, complex chemistry, so on chemistry. In a nutshell, if you do electrochemistry, if you're interested in that, it's clear soft X-ray spectroscopy is really very powerful to learn about molecular constituents, both in water plus interfaces, molecular solvate solution issues, be it charge transfer, be it classical catalytic processes, so on. I think the conceptual understanding of X-ray matter interaction hinges on our description. How do we understand the valence electrons and the core electrons? And in a very simple way, the core electrons help us to project valence electrons onto atomic sites. That's cool. And we learn about the different chemical species, oxidation state, spin state, you name it. And a very powerful concept is the equivalent core approximation. Think about the chemistry of the core ionized signature, if it's XPS, NEXAFs, as if you had the next element in. The nitrogen replaces with the oxygen replaces with the fluorine. And if you think about it, it becomes clear. If you take a water molecule and you replace the oxygen with a fluorine, of course, HF is a stable species. And of course, the second hydrogen is trying to fly away, right? And so if you think about it, it's clear if people had thought about water and X-ray spectroscopy a little more in the beginning, it was clear that core excited oxygen behaves like fluorine, which chemically is a HF species. And therefore, there gotta be a hell of proton dynamics in it. And a lot of the mistakes about the split peak and this and that wouldn't have come up and wouldn't have misled a ton of the effort in somehow crazy directions. But okay, spilled milk. The thing is, when you get engaged in this, think about it. It's powerful, but it's also limited because the next level is Hartree-Fock Slater transition potential, which is very easy to do, which is embedded now in a lot of programs in ORCA, in Gaussian. You can just calculate on your laptop. And if you look at X-rays, ESCA, electron spectroscopy, NEXAFs, use these tools. This is what's behind the so-called transition potential method. It's an approximative trick which you get in by Taylor expansion of the total energy difference. And then you get this fractional occupation, and then you can calculate this very easily on the laptop. And it's powerful, and you learn it. You should be aware it's an approximation. And then comes the next circle of hell, which is the dynamics of X-ray matter interaction, because it's a resonant inelastic X-ray scattering process. And this has the consequence that we, for one, of course, can select on resonance different species, but we should not forget that being on resonance means scattering duration time plays a role. And so we can play the game of detuning, which helps us to quench this away. And it often, as an experimentalist, gives us a feel where we measure fluorescence, detune on the lower edge, and you will find out, look, some peaks get weaker. And then you should think, maybe that's really the dynamics, which is just in the X-ray process. And that's the lesson learned from the water studies. Actually, there are not two peaks, it's only one peak. And this, of course, has repercussions then on how you look at it, how you should normalize. Sometimes it's better also if you measure X-ray NEXAFs, also absorption. It's very good to measure longer because on the long trace, the atomic cross-sections come out independent of chemical environment. And if you cannot get your curves on top of each other, you should measure longer because they must come together on the long range. And if they are not, then there are reasons. In water, it's the surprisingly strong second solvation shell scattering, which really wreaks havoc to your normalization if you don't go higher. And for that reason, the hydrogen bridge bonding number was significantly wrong, thought for a long time for liquid water, and fortunately could be corrected. And that's what I've then discussed a little bit to give it a little more science. Okay, we do, I think it is fun to measure liquid water, the number of bonds. We understand a lot about the thing. It makes sense, of course, to finish the thing. Nobody still knows very well the second critical point of water in the super cooled region, the so-called no man's land. It is conceptually very hard. I think people are working hard towards it. In principle, you can do the same experiment that we did on silicon, basically melt with a laser frozen crystalline liquid water and see how it goes through the transient phases. And this will sooner or later, hopefully now resolve the issue. And we can actually find these transient phases and the second critical point of water, which must be there. There is no reason why it should be there, because it's there in any of the tetrahedral solids, silicon, diamond, gallium arsenide, germanium, you name it. So water must have it. And I think these are great tools: equilibrium, non-equilibrium dynamics. I think people which are directly involved, I think, in the water research, which is, of course, Johannes, Vinicius, Sebastian, Annette, Mattis. You know, there's a lot of technology, liquid jet operation cells, electrochemical cells. I mean, you know that none of these things just works for free. The Paul Scherrer Institute has been playing an important role on measuring this first high-resolution RIXS spectra on water. And Thorsten Schmidt and Vladimir Strokov have been super important in being able to do that. And then there's a massive computational side, which has been very, very important to understand this on a solid basis, because it has been extremely confusing. And it was not clear that it ever got clear. And I think everybody in science has this moment of depression when you think, I mean, we will never understand what's going on. And so I think we experimentalists, we are all extremely indebted to Faris Gelmo-Kanov and Michael Odelius and their teams, Christoph Sahle and Chris Gilmore, to really not give up and help us also conceptualize. With this, I thank you, and I thank Andrew for having the opportunity to talk to you guys here.
Thank you, Alexander. It was an amazing talk. I think you explained a lot of concepts very clearly. And just for the audience, I want to mention that we also hosted about a year ago Anders Nilsson, who also discussed just specifically water, not within the RIXS, without the RIXS specifics, more on the XFEL side, but it was very important also. A very important talk for the electrochemical community.
Yeah, he's a great guy. He was my thesis advisor, Niels Mortensen and Anders. I was doing my PhD with these guys. And Anders is doing a fantastic job trying to find the second critical point, mostly by diffraction, to see that the correlation as it changes, as we go transiently from ice through these phases. And I think he has first indications in this direction. And I said, every tetrahedral solid must have the supercritical liquids. It's a tough thing because it just resides in this very nasty homogeneous nucleation region where the devil is in the details. But I think it's a fantastic time. And finally, all these things come together. And I think, you guys potentially were doing a career in water splitting, in water-based technologies, electrochemistry. I think one can, from their point of view, one can almost take it, I think, for granted that these fluctuation exists, but also these additional phases really exist. And one should be aware of it.
Mm-hmm. And maybe I can start with questions, and we're open, of course, to questions. Feel free to raise your hand if you want to ask a question. You mentioned diffraction. So how do you see the spectroscopy complementing diffraction? Or is it just another way to probe exactly the same thing?
There are links. Diffraction, as you know, measures, obviously, structural properties. And for time resolved on this specific problem on trying to measure a transient species, I think it is very powerful. The trouble is diffraction doesn't tell you about the different chemical species. So you measure the average distances of oxygen atoms, but it has a very, very hard time to tell you if now these oxygen atoms have a correlation length in a statistical distribution, or if they have actually different patches of chemical composition that in a powder diffraction logic, in a way, gives you similar signatures. So the spectroscopic thing, why we also push on this like crazy is, can one actually find these different species? Nobody disagrees that the liquid water phases have different correlation length, but what we try to find, are there different groups of potential energy surfaces? Because that would really indicate that it's not all statistically distributed, but it really has a structuring thing, even though it's fluctuating. And that only spectroscopy can, I think, or has the hope to piece that together. I think none of it alone can in the end. I think a lot of points are pointing towards it. This super-cooled phase physics is really a general feature. And that's why the purported critical point, which Angel and Sastry predicted already in the 80s at minus 22 degrees Celsius, is there. I think there is very little doubt. But the problem is now experimentally, you would like to get it really beautifully shown. Yeah. But I think in terms of complex system physics, there's little doubt. The sad thing is Angel, who in a way promoted that thinking, he died recently. So nobody gets a Nobel Prize anyway, because the guy who said that first, he just happened to die. And Röntgen is dead like hell either. So, but what the hell? It's just fun to find out what's going on.
Okay, Peter, go ahead.
Yeah, thanks again for very nice overview and very interesting details. I have two questions. One is regarding the results you elaborated very well on the difference between the three spectra that you showed, so the EELS, then the XRS, both for the liquid and gas. Yeah. Yes, so this, yeah. And I was just wondering, did you measure these things under the same condition?
Yes, you're completely right. Why these things are measured in different ways is, maybe I jump back. Just close your eyes. I say when we're there. This is a terrible flight through a million slides. Here. The problem is we measure a scattering plane. And we need to get the correct number of unoccupied states. As we discussed here, to measure the absorption, the true absorption, the atomic cross-section as a function of energy is a very difficult thing. Because in principle, you can only do it in a transmission experiment where, I mean, Lambert-Bear's law says the sample has to be optically thin, and we must not have self-absorption, which is the mismatch of the excitation volume to the probing volume. And as you see here, this is a model study of chromium in oxygen in water. It is very, very difficult to really measure absolute cross-sections, right? It's always easy to somehow measure something and then somehow say, oh, it looks a little different, it looks a little similar, there's a little shift. But to get the number of electrons or the number of holes right is excruciatingly difficult. And so what we did for the water experiment, water ice gas experiment, we basically worked very, very hard on the sample environment to get an absolute measurement of cross-section in a true Lambert-Bear transmission experiment, right? And this is really the big problem. And so the NEXAFs, the assignment of the number of hydrogen bonds in water based on X-ray tools has been hampered by two things. One thing was the thing people measured too short because they thought there cannot be such a strong scattering resonance, which is also surprising. I mean, that the second coordination shell has such a surprisingly strong, but the reason why it is because there are so many water molecules in the second shell. So they add up in the end to a lot of scattering, right? And that was the one thing. The second thing is people were a little lighthearted in taking partial yield measurements, basically fluorescence yield, just put a photodiode somewhere and measure some yield, and then just say, well, let's just take the intensity as a number and say this is now the number of states. That really was the second issue, that people got sloppy with thinking, is their measurement truly a Lambert pair? And if you look now on the slide we're looking at, on the lowest, the bottom figure, right? That's typically a fluorescence yield measurement you do, and you see the massive deviation you have from a true Lambert pair absorption experiment. I mean, you kind of see the peaks, but the intensities, I mean, you can smoke them, right? And so I think there are really two lessons learned. I mean, if you want to do a comparative study, for example, if you have an electrochemical cell, right, and you do a cyclic voltammetric measurement, right? I mean, you cycle the cell, and then you measure NEXAFs as a function of voltage. You see the relative changes very well, right? I mean, you can very easily do a comparative thing. You got to be super careful if you want to really count the number of species. For that, just doing a fluorescence measurement is not going to do the thing. You really got to work on getting to a Lambert pair condition.
So in terms of experimental setting, then they were done in the same way. That's just what I want to know in terms of experimental setting.
No, they're done in a different way in order to have a Lambert pair transmission behavior. I mean, okay, the liquid and ice.
EELS, if it's the EELS that I know, right, you need vacuum, right?
Exactly, but this is gas phase, and you make basically a cell where you can propagate and you can control extremely well the parameters, the cross sections, and this and that, right? And the same you do with the liquid and solid, which is actually a hard X-ray Raman experiment, where you measure on a very hard X-ray 20 kilo electron volts the Raman loss from the core valence excitation, and by that your sample becomes optically very, very thin because the penetration depth is huge. And that is exactly the thing. So, I mean, if you read these papers, I mean, you realize that the trouble, and this is, I mean, you can call it the good or a bad side, but the reality of classical X-ray spectroscopy is chemical shifts are great to quantify and understand. It gets trickier if you got to be careful, obviously, when you do a fluorescence measurement with dynamics of the core excited state, as was exemplified with a water problem and the split peak, which actually is just proton dynamics, which you understand why, because HF wants to get rid of a second proton. And then we have to, I think, acknowledge that we have to be very, very careful when we try to assign, when we want to count stoichiometric ratios out of simple fluorescence measurements. That seems to be very dangerous for the simple reason that we have, it's basically impossible to do a fluorescence detection which is fulfilling the Lambert pair condition, unless you have a thin film sample, which could be a thin liquid jet, which could be a monolayer in a sample. If you like have if a glass substrate and you grow a very thin film of your material, yes, you might fulfill the thin condition. But as long as a thick film, you don't, right? And typically what you measure is what we have here on the lower bottom. You have something which is somewhat getting already good towards the true cross-section of absorption, but it's significantly distorted in intensity because it's a combination of self-absorption and true absorption.
Yeah. Maybe
I just want to make you guys aware of that, that, you know.
Maybe one related question and last one from my side is we do know that also the water interacts with the X-ray, and then if you use, it says 20 keV to excite the water.
You know, it's no, of course, all these experiments are done in by replacing the sample. I mean, the soft X-ray is a liquid jet, which is a glass nozzle, which has a 30 micron diameter, and then you make a liquid of 10 micron, which is rapidly flowing with 6 meters per second. So you're continuously replacing the sample, and so on and so forth. And the same you can do it in XFEL. You have 2 liquid beams which kind of cross, and then they span a liquid sheet. Like when you have a water tap and you put a finger on, you can kind of stretch out a liquid sheet, right? And the same you can do in vacuum by crossing 2 fast-running liquid jets, which also then span a liquid sheet, which is only like 200 nanometers thick. And this thing, you can measure the thickness by optical interferometry between the back and the front of the liquid. And that gives you the thickness of the sheet. And then you can measure the transmission, which is then the absorption through a defined liquid sheet thickness. So there's a lot of technology behind this, of course, that's true.
Okay, so then the interaction of the X-ray and with water doesn't really influence what you measure in that case. So the water is not maybe...
Very good point. On a synchrotron, let's think about it. I mean, a synchrotron creates about 10 to 10 or 10 to 11 photons per second, right?
Yeah.
And it has a repetition rate of maybe it depends on the synchrotron now, typically 500 megahertz, like also a few hundred megahertz, right?
Yeah.
So that means undulator pulse has about 10 to 6 photons per pulse in the focus, right? The cross section is easily 10 to minus 6. So one synchrotron pulse, as a matter of fact, I mean, I have a million one synchrotron pulse, therefore, really creates about 1 core excitation in your sample, right? So each time, I mean, you know, the synchrotron is a pulse source. Each pulse has, even on a very bright undulator, only so many photons, about, I said, about 10 to 6 per pulse, which is less than 1 core excitation in the whole focus for 1 pulse. And for that reason, actually, X-ray spectroscopy, I mean, all synchrotron science measures impurity detection, and that's why we get away with like a lot of ground state logic. Only if you go to a free electron laser, you start to have actually 10 to 12 photons per pulse, which means you have in an interaction volume 10 to 5 excited states at the same time. And then you do stimulated emission and you go into a nonlinear process. And there's a deep link between spontaneous inelastic X-ray scattering and stimulated X-ray scattering. We could work that out, but it's a lecture on its own. It's a lot of fun to think about it. And this is why on an FEL experiment, you have to rethink your measurement strategy significantly. Because what happens there is that the RIXS process works in the following way. You make a core impurity state, and actually, what makes this core excited state decay? It's a very interesting thing. The reason why the core excited state decays is because there is black body radiation. we are sitting here and there's continuously vacuum fluctuation and black body radiation. And the black body radiation is everywhere, even in the vacuum. So the core hole, the core excited state, is always impinged by black body radiation of every frequency. And to a very small probability, even with X-ray radiation. And so the X-ray, which comes out of the background, the black body background radiation, stimulates the decay of the core excited state and makes it create X-ray fluorescence. And this is why we have why this is a natural constant, because the black body radiation is the same everywhere, in vacuum, in liquid, in solid, in you name it. So as soon as you have a core excited state, the probability for it to decay in fluorescence is the probability that a black body photon hits it and stimulates it back down. The other thing which competes is the Coulomb field of the nucleus. The Coulomb field of the nucleus also creates a Coulomb field which the electron sees, which makes it fall down in a Auger decay. Because this is not a dipole. The dipole can only happen as a duplication of a black body photon. If you now go to a FEL, the black body radiation field becomes weak in comparison to the FEL field itself. And therefore, the FEL not only excites it, but it also pumps it back down. And for that reason, on a FEL, there's always a very high competition to core excite and go back down, which we call stimulated emission. And the stimulated emission then takes over. We published a bunch of papers. I don't have the backup slides because it's another hour of talking about stimulated emission, but it's very, very interesting. And so you're right. But as long as we are on a synchrotron and we have 10 to 6 photons within the scattering duration time, we are in the limit of single scattering in the whole illuminated region. And there is no risk of any collective excitation and de-excitation.
Yeah, thank you. Thank you for, yeah.
Thank you, Alexander. That was fairly explicit explanation. I also have a few, maybe a couple of questions before we wrap it up for today. 1 second. So one is related to the renormalization of the spectra that you showed previously. So there, I'm just curious, is it possible not to be going into this long energy tail, measuring every energy, but just going, say, plus 50 eV there, measure a small range, and that's it. So you don't have to consume time for this, and so making it.
You know, you're completely right. It has been, and I think I completely agree, in a classical NEXF spectrum, 15 to 20 EV above the edge, you already converge into the sudden limit. And that is completely normal and the way it is. In that sense, the surprisingly strong second scattering resonance for water was a huge surprise and is not prototypical. So it continues to be correct. If you just measure a NEXF, 50 to 20 EV is completely enough if you want to characterize different oxidation states of iron and this and that, because they truly coincide very rapidly. However, I think the personal conclusion to it is, I mean, it might be time well invested before you standardize your process and you say, let's measure now a whole batch of samples on that, to really cross-check on 2 extreme cases where you kind of know. You know, because, I mean, even though I think we all thought, I mean, come on, this should be plain vanilla, it turned out to be a huge trap. And so, you know, I mean, I guess typically one embarks on a series of materials which one studies on, I would really say take the time to measure two, 3 cases where you know they are definitely chemically very different, and see how far up you would go until they collapse, and that gives you certainty about the normalization.
I see, but in this case, I'm just curious also about this, because for water, so you mentioned that deviations are because of the second coordination, but the second coordination should be quite accessible. I mean, something like this should be known, right? So people should know about this.
That is true. Nobody just thought that this is visible in this X-ray spectroscopy.
I see. So
right?
It's because,
because typically these scattering resonances are rather weak. And that's, I mean, there is a topic of the so-called shape resonance in XFs, and it's usually powerful, but it usually is the first scattering resonance, right? It's the next neighbor. And the next neighbor everybody has on the agenda, I mean, it's typically about 10, 15 EV above the lowest state. And this is why you go a little higher and then you're done. The fact that here we have to go significantly higher is, the first and second coordination shell of water has been measured, and it has, of course, also this how do you call this? The singularity around 47 degrees Celsius, right? Where the second shell kind of starts to disappear. And this is known by Skinner, who made, I think, already in the 80s, a beautiful experiment about that. And so the funny thing is, nobody was linking back our knowledge that the second coordination shell exists to, is it actually an observable here also in X-ray absorption? Since if you do a classical solid or something which is a little tighter coordinated, you typically get a shape resonance and then you're done with it. And this is good.
Okay.
So I said, I think we shouldn't get paranoid out of it. I mean, water was definitely teaching a lot of lessons, for better or worse. I would still say, as you said, yes, classical NEXAFs is completely okay to measure the unoccupied states, the ionization potential, the shape resonance, and then go a little higher and say, this is now continuum. Let's be happy. But I said, I wouldn't be completely naive about it. So if you measure, say, we have a lot of different samples which contain always the same element in different concentration or preparations, I think it's not a bad idea to just measure some 20 EV more and really see, do they really go together?
Okay, that makes sense. And if this is a good signature, would you say that if we have a sample where we have a significant density of interfaces between a solid and, say, an aqueous solution, then this is something that we may be able to sense in that, so be able to distinguish?
That's a super good point, and I'm wondering myself about it. So for that reason, exactly, we're also trying to understand in a complex which has solvation shells, can we actually pick up these higher solvation shells also in the signatures of the complex metal atom, but of course also in the interface? How does the Helmholtz layer, I mean, the ordering of electrochemical dipolar order, so to say, what are the signatures of that? And I agree, if I was like spending a lot of time in classical liquid interface issues, that is clearly a study one could systematically try to understand better. If this is actually a feature, a bug, or if it doesn't play a role.
Okay. So my last question is about the future. I'm just curious if you showed so many new facilities that are building. Where do you see the future of this? Because this field is, I think for a long time, it's been a pretty niche field, and now it's being expanded. Quite a lot of people are trying to use these RIXS techniques, both in hard X-rays and soft X-rays. Where do you see the future, say, in 10 years? Everyone will start using XFELs in that configuration, or in RIXS configuration, or would it be just not a lot of things that we can add, let's put it this way, on top of what we have, and we just need to keep using it?
Andrew, it's a very human question, and I always relate it to this aspect. If you asked me on which stocks you should invest in order to have a great return in 10 years, and I would tell you this and this and this, you would laugh at me and say nobody knows that. And that's one side. I think we as scientists, we currently live in a situation where a lot of people claim that they can really predict. It's also expected from us more fundamental scientists to deliver predictable results. But I think we should first of all take the liberty to step aside and say we are a little bit, of course, we want to analyze and create great tools which give reliable results. And that synchrotrons and standardized techniques are hugely helpful. And I think the reason also why this becomes more popular is because we have a more standardized understanding how to look at it. And because the computational tools with readily embedded, transition potential tools and all this type of things, just make it accessible to kind of get a feel what you measured there. That's very good. And this will simply make it possible to look at interfaces, buried systems, liquid, solid, colloidal, complexes, you name it, right? And it's true, on an FEL, you have amazing many photons. But as we just started to bring up, I mean, you partly also do different physics because we go into multi-photon processes. So I think if you are interested in materials and analytics, it's definitely a thing where the spectroscopy should step back a little bit from the focus of attention, and people which have real interesting sample problems can benefit. And therefore, I would say it makes a lot of sense to engage first with systems where you kind of know what happens and try to understand for yourself what you did, and then broaden your scope into true questions, right? And I think it's a good time to get engaged and spend time, because the field is clearly not closing. It's always good to get into a field when there's some basis, and then it opens up to a broadening in terms of systems. And I think we're at that time. What systems in the end is going to be breakthrough is really hard to say. Is it going to be Grätzel cells? Is it going to be charge injection? Is it going to be, classical interface electrochemistry? But the topic is super interesting, and we can finally look at it not just in average potentials, implicit solvation. We can do explicit solvation. We can see on the molecular level what's happening, and that's just pretty damn amazing, I'd say.
No, I agree. That's very, very good. And I think that probably the pump probe experiments will be somewhat, from the instrumental point of view, might be some of the next steps that people will be more and more exploring. Because so far it looks like it's a fairly, again, it's a niche part of where experts usually use these techniques, but maybe that will get more widely explored.
Pump probe is not only photochemistry. I mean, I think we all have to acknowledge, and we should never forget, photochemistry is a few percent at best of any relevant reactions.
Yes.
And it has been largely driven by the ability to do technically photochemistry with lasers and these type of things. But photochemistry is also, as a pump probe tool, is also a great way to generate suddenly heat jumps, to generate suddenly charge injection, to generate, exactly, conformer change. And most likely the future of pump probe is not so much basic photochemistry, but to really use it as a trigger to study thermal processes or statistical electrochemical processes, but to kind of get them into into an ordered scenario where you can pick up the transients and not only ensemble averages, which is of course in equilibrium difficult to separate.
Right. So for the electrochemical, this is why I was asking it, because for electrochemical interfaces, this can offer a lot of opportunities. Before we hosted Richard Koopman, and he was giving a talk on not X-ray pump probe experience, but just the visible light pump. But those were very, very insightful reactions. I can imagine that in X-rays that could be expanded even further. Although it's tricky to do, very tricky.
Oh yeah.
Okay, Alexander, thank you so much. Thank you a lot for this very long discussion, and of course an amazing talk that was. But I'm really excited about so many details that you were eager to reveal.
Thank you, Andrew. Thank you, everybody. It was really fun. Great pleasure.
Yes. Have a nice evening. Thank you.
Thank you.